Hello everybody, welcome to physics. This is the day before the big energy test. We're going to try to tie up any loose ends that we have. Okay everybody, so the question is this. It's about the spring, and it's going to land a distance away from the table because it's going to pick up some kinetic energy at the end of this K. The spring constant is really what we're going for here, so that's what we're looking for. But we know that this kinetic energy right here is equal to what? Kinetic energy at that point at the edge of the table is equal to the potential of the spring, right? So 1/2 mv squared is equal to 1/2 kx squared. Okay. Okay, so if we knew what our velocity was, we could say that cancel these out, and our spring constant then is going to be equal to mv squared divided by x squared. And we have all those variables except for we don't have v, so this isn't valid because it doesn't say we can do it in terms of v. So now we have to work our way backwards. So this distance here is a product of the velocity in the x direction and the time that it takes to fall, right? So we can do it in terms of d. So right there we see that we're gonna somehow get our v out of the equation because it's going to be in terms of d. So how long does it take to fall to the ground? Well, x equals v sub naught t plus 1/2 at squared, and our initial velocity in the y direction here is 0. So our h, which is our x in this case, is equal to 1/2 at squared. And I believe we said we could do it in terms of little g, right? Okay, so it'd be, t then is equal to the square root of 2h over little g. Okay, so now we have our time. So if we look at this, we can solve for velocity in the x direction, and that would be then d divided by the square root of 2h over little g. And that could be our definition right there of velocity in the x direction. Do you agree with that, everybody? Okay, so now that velocity is going to come out from this spring energy, right? So this velocity here then is that velocity. So if we want to plug that in, we can have a better answer for the spring constant. That's a little k, is equal to okay, so you just plug in here and do a little bit of algebra, and I guess the final answer then is md squared g over 2hx squared. And that should be our spring constant unless I messed up on the algebra. Okay. Another part of that question then was the work done on the block. And so is it the work done on the block total or the work done on the block after it leaves the spring? So the work done on the block by the spring, that's real easy. Because work is force parallel displacement, right? And work equals Hooke's law says the force is negative kx. Do you agree? So kx times d. But that's your maximum force, so that only happens like right there. But at this part, it's 0 force. So the average force on an ideal spring is half of kx. So work then equals 1/2 kx. D is the distance over which the force is applied, which is really the same x. So work is equal to 1/2 kx squared. We also call that the potential of the spring. So since we don't have k, the work that the spring does is 1/2, and then our solution was for K?
mv squared g over 2hx squared.
So that's all x, or that's K, right? And then x squared again. So that would be the non-simplified version of work, which would get you your 5 on your AP test. But you could just cancel this out if you wanted to. Work then is 1/4 md squared g over h. You can put it like that too. Okay, so the question here is, what's the velocity at the bottom of the ramp, right? So we know that velocity here is going to be, related to the kinetic energy that it has, right? So the kinetic energy at the bottom of the ramp is going to be 1/2 mv squared. Well, where does that kinetic energy come from? Well, we can talk about force parallel to displacement, and that would be the work on the box. Or you can talk about force parallel to displacement, which would be equal to the change in potential energy. But none of those are kinetic energy in this case, because we have friction that takes away from mechanical energy. So there's conservative forces, there's non-conservative forces. The conservative forces are called mechanical forces or mechanical energy. Non-conservative is that constant random motion increase of the particles on the surface called heat. And that happens when friction works on an object. So friction always takes away from mechanical energy. It's called non-conservative. So in this case, the kinetic energy is not equal to potential, but is equal to potential and what else? Minus the work due to friction. Because all that energy went into the movement of these particles on here and then on the bottom of the box. And that is non-mechanical because it's going all directions at all times. There's 6.02 times 10 to the 23rd pieces in, a cubic centimeter of an average substance. When you start jiggling those pieces around, it's going in all directions. It's non-mechanical. Mechanical is like kind of in certain directions, kind of. Although energy doesn't have direction. So, is that enough to help you? Okay. Okay, here's another situation. We're talking about work done. So if we're talking about moving this crate in a distance or a displacement, and we're trying to figure out how much work is done here. Or maybe we're trying to figure out how much velocity we have at the end of this. If we say that v sub naught equals 0, we could figure out a velocity here too. But notice up here we have friction. So the work that we do is not turned into kinetic energy necessarily, but the work that we do is turned into kinetic energy plus constant random motion, or increased random motion. Increased motion of the random movement of the particles, the two surfaces that are interacting. So, in this case, we could say the work, so maybe I might say, what's the work that you did? Okay, well in this case, what would you say the work is that you did? So that's the force that you apply that's parallel to the displacement. So in this case, the work that you do, if you're pulling on this thing, is going to be cosine theta t. That's the force that you apply that's parallel to the displacement. This is then the definition of the work that you did. Okay, so then the next question is going to ask something like, well, okay, that's the work you did, that's right. What's the kinetic energy that the block has at the end of this work if we start at an initial velocity of 0? Well, what's the formula for that? Okay, so the kinetic energy that this block has is equal to the work that you do minus friction. Right? So the work that you do, part of that work is going to go into moving these particles more. That's the friction part. But the other part of the work is going to come out in a velocity here. So kinetic energy is the work you do minus the force of friction. That is called the net work kinetic energy theorem. Okay, so in this case then, kinetic energy is cosine theta t d minus coefficient times the normal. Is that good enough? No. We got to break that down. Kinetic energy is here. Finish this expression for me. Okay, so it's cosine theta t d minus the coefficient times mg, which this is the mass, mg minus sine theta t, and that is the kinetic energy. And then you could set that equal to 1/2 mv squared and figure out the velocity. Yeah, thanks for that. I screwed up. This is just the force of friction. We also have to multiply that by the d to get the work that friction did. So this is the final expression that gives you the kinetic energy, and then with that you can solve for the velocity. That's the work of friction. So I have a question for you. Let's say that I have a spring here, and let's say that this right here is equilibrium. Okay, so it's going throughout this stretch here. We'll call this x. Could you define spring constant here? So work around the potential of an energy, or potential energy of a spring formula. Solve for K with this picture. Yeah, so according to this picture, this thing is bouncing up and down. Because if this thing wasn't moving, it would be, the block would be right in the middle here at equilibrium. Okay, so can you come up with a definition for spring constant? Well, let's just look at it together here real quick. Potential energy of a spring is 1/2 kx squared. So the k then would be equal to 2 times the potential energy of a spring divided by 1/2 x squared. Oops, the 1/2 is squared too. Okay, I got a question for you. Let's talk right here. Talk velocities here, here, and here, or wherever the top is. Which has the biggest velocity? Equilibrium would have the biggest velocity. Here the velocity would be equal to 0. Here the velocity would be equal to 0 too, right? So which has the biggest kinetic energy? This one, right? Because it has the biggest velocity. Here there'd be no kinetic energy. Here there'd be no kinetic energy. Which has the biggest potential energy? Okay, so here, so without going too far into this, we would say that this would have the biggest potential, this would have the biggest potential, and here there'd be no potential, right at equilibrium.